So now we're going to be doing the calculus version of exponential growth. So we're going to do everything we've done in pre-calc before with exponential growth, but now we're going to add to it a little rate of change at a certain number, which means we need the derivative. Well, the only thing that we're taking the derivative with respect to here is time. So we're getting the rate of change with respect to time. So t is our only variable that we have to look at when we do these problems. So we end up with a0 e to the k t. That's our normal derivative. It doesn't change. However, we do have an exponent that can be derived. So if I write that, you can see the coefficient for our t is k. So we times by k. So what we really end up with is this, k times a. So it's the original function times k, because that's all that's happening is whatever the exponent is, it just goes in front. Okay, so now let's try one of these problems. So a cell of bacterium divides into 2 cells every 10 minutes. This means that it doubles every 10 minutes. The initial population of the culture is 100 cells. So if you remember, a sub 0, that is our initial amount. So when they say that, we already know what our a sub 0 is. So we can plug that in. So we have a, I'm just going to use a now, not a of t. And that's 100 e to the kt. So this is what we know just from a sub 0. Now we also need to find k. So if you remember from these exponential growths, k is our growth or decay rate. So if it grows at a continuous rate of 4%, you'd put in 0.04 there. If it continuously decays at 4%, we put in 0.04 with a negative on it. And that's from the previous videos. So what we want to do now is find that k. So that's what it's asking. K equals what? Well, what we do know is that at a of 10, our amount has doubled. So if it starts at 100, it would now be 200. So if we plug those in, our t equals 10 and our a equals 200, you'll see that we are left with just k to solve for. And so now we have an equation that we can use to solve. So I'm going to rewrite it. 200 equals 100 e to the 10k. And you guys should know the steps by now. So we just divide by 100. And there's our 2. And it should always be 2 because it's doubled. And then we natural log both sides. So ln of 2 equals 10k. And then we divide by 10. Now if you've done this enough, you could have already just said, well, k is ln of 2 over 10. Because it's the time it takes to double. So ln of whatever you want and time to take to get there. So if we wanted to be, we want to know how long does it take to get to 1.5. It's ln of 1.5 over the time it takes to get there. All right, so that is now our k, and we're going to leave it the way it is just to make it more usable. So now let's plug it in to find the expression for our numbers of cells. So we have 100 e till ln of 2 over 10 t. And you can see this is not very nice. It's very messy looking. So what we're going to do is a little modifying first, and then we're going to come back and replace that. So let's get rid of it now. And we come back over here. We can use our log rules. So if I make this a 1/10 ln of 2, this now will become the exponent. So k equals ln of 2 to the 1/10. Now when I plug it in, what do you get? Well, we end up with this, 100, and we're going to put parentheses around it now, e ln of 2 to the 1/10 to the power of t. And so you know the e and ln cancel because it's e to the ln. So it's 100, 2 to the 1/10 t. So now what does that tell us? Well, 2 to the 1/10, if we plug it in the calculator, is 1.07. This is 107%. So we're getting a growth rate of 107%. So every minute, we add 7% basically to it. 7% of what it was previously. So this is now our new formula. And a, we go back up and see what it is. A is the number of cells. And you always want to define your variables when you have a formula. T is time in minutes. I know I have it on there as t is in minutes is all I wanted to write, but I wanted to put time in there. So now you know it's time for t. A is the number of cells. So we can now use it. Find the number of cells after 2 hours. Well, t is 2 hours. That would be 120 minutes. So it allows us to convert if you already know the time. So a of 120 now, we just plug in. And you already have kind of an estimate of this. We know it doubles every 10 minutes. So there's another formula that we can get. You can see here that it's t over 10. That is a doubling formula. All right. I didn't plug in the 120. Let's go back. 120. So now we just plug it in the calculator. 100, parenthesis 2, and then now you can just put exponent t over 10. So that would just be 120 divided by 10, which is 12. So 409,600 cells. It also tells us what to use for the units since we're finding A. And so what's happening here is, you think about it, if it's 120 minutes, if we rewrite this is 100 to, I've got to explain everything. You want to know everything about a problem, not just how to solve it and how it works. But the more you understand it, the better you really understand these problems and the simpler they get. So you can see that our problem actually doubled 12 times here within 120 minutes because it was 10 minutes, it doubles. So within 120 minutes, it'll double 12 times. That's what's happening. So you see, all the math here works perfectly. So this formula works, this formula works. If you had calculated a decimal for that and plugged it in up here, it would still work. All right. So now what we want to do is find the growth rate after 2 hours. And I like changing that immediately to at 2 hours because we are finding an instantaneous. So what they're asking us to find is the derivative. So a prime of t is just equal to k times a, right? That's our formula. So you can use that one, and our k is up here as ln of 2 to the 1/10. You see we have it right there. K is ln of 2 to the 1/10. And then our a is given right there. It's 100 times 2 to the 1/10 t. So that's our formula. It's just the k times that. But you can also just take the derivative. So we already have the formula up there. And it's a is equal to 100, 2 to the 1/10 t. And I'm going to leave it this way. And so you can see now that this is our exponential. We got a nice clean t. So the derivative of this will just be 1. So we take the derivative, and that would just be rewriting it exactly how it looks. Right? Times, now this is not an e in there, so we've got to put the natural log in there of 2 to the 1/10. So you can see that is just our k here. So whatever is inside is the k, and we just put it here. You can see it up here as well. See, 2 to the 1/10, and there you have it. There's ln of 2 to the 1/10. What was our k? ln of 2 to the 1/10. Here, let me just zoom in this way to show you. Okay, so however you do it, it's fine. You can even say, you know what, I just like having this as a decimal, and I'm just going to keep the decimal and do it that way. Completely fine. It works exactly the same way. So you could even just take the derivative of this one, and it would work exactly the same way. Because if you did the e, it would be 100 e to this, right, which is this, times the derivative of the exponent, which would be ln of 2 to the 1/10. And there it is. So all the formulas work. Whichever one you want to use, they work the same way. But we need to make this look a little bit nicer. So we get 100 ln of 2 to the 1/10, put parentheses around it, times 2 to the 1/10 t. Now, all we have to do is plug in the time, and it's going to tell us the rate of change. But first, let's find our units. So we have dA over dt. And so if we go back now, we already know A is a number of cells. So it's cells. And T is time in minutes. So now we know our units. Whatever we get, it's cells per minute. So now we're just going to plug 2 into this function. So 100 ln 2 to the 1/10 times 2 to the 1/10 2. And we'll see what the rate of change is at 2 hours. What? That's 120 minutes. So see, we got to pay attention to this stuff. 2 hours is actually 120 minutes, just like before. So we're looking right now, it's at 409,600 cells. How much will it change at 2 minutes? So let's take our calculator and find out. Move this over a bit, bring the calculator back up. All right, so it's 100 natural log, and take your time. There's no reason to rush on this. All right, let's double check it. It's 100 natural log of 2 to the 1/10 times 2 to the 1/10 to the power of 120. And we get that 28,391, 28,391. So 28,391, and then we got to put the units on there. That's what makes this important. Cells per minute. So what it's telling us as an approximation that we should expect over the next minute another 28,391 cells, because you got to think it's doubling every 10 minutes. So we're at 409,600 cells. In 10 minutes, we'll have twice as many. So over 800,000 cells at that point. So that's a lot per minute. Now, if we were to plug in the next one, which is 121 minutes, this would probably go up. It would. And if we plugged in 122 minutes and so on, same thing. So what's the question now? When will the population reach 1 million cells? Well, we already know 10 minutes later it's going to be at 800. So it should be around 130 and 140, somewhere in that range. So let's see what we get. Well, what we're saying here is our A is 100 is a million. So I'm going to put all the zeros in there like that. And so we take that and we plug it into our formula. And that's the one up there. Jeez, I forgot the zeros. So 1, 0, 0, 0, 0 equals 100. 2 to the 1/10 t. You know, when you're doing a video and there's this many numbers to keep track of, it makes you a little nervous. All right, so we solve this exactly like we did when we were finding k. So anytime you're looking for an exponent, you divide ln ln. Okay, so we're going to divide by 100. We kill off 2 zeros. So we have 1, 1, 2, 3, 4 zeros now. So that's 10,000. All right, and you can use log if you want, but I'm going to use natural log, ln, ln. So we have ln of 1,000. You can even rewrite it into exponential form, but I like doing this. So this would be now t over 10, ln of 2, and then we divide. And we multiply by 10. So like that, cancel, divide. All right, so there we go. That's our time. If we plug that in, then we should get something like this. So if we think about 409,000, it takes 10 minutes to double. So at 1:30, this would become 800 and something. So, and then you probably get another like 30,000 or so on there. So probably like around 135, 134, 133, somewhere in the 130s, because 10 times more. But if we're not going to go to 140, because that's going to be 800 times 2, which is 800,000 times 2, which is 1.6 million. So too much. So let's plug this in our calculator and see what we get. But we're just estimating to know that we're correct. And it's 132.88. So 132, I'm going to put the decimal on there, 0.882, and then our time is in minutes. And so you can convert this into hours if you want. So this is 2 hours, right? And then 120 minus 132 is 12 minutes. So just say 13 minutes, because we want to get it to that point. So about 2 hours, 13 minutes in order to get to 1 million cells. And there you go. There's all the questions wrapped around one problem. So we find the k, we find amounts at a certain time, we find the time it takes to get to a certain amount, we found rate of changes. I think we're good. There you go.